All right, well, let's see. I think we've covered the key ideas for figuring out the magnetic force on a test charge or a test current, both magnitude and direction. Does that make sense? Anything else? Ah. What is the direction of the magnetic force in this problem? The direction of the magnetic force.
Well, you know, it's going that way. B is, I'm not really sure how to do that with my hand.
Now you've skipped a step. Remember that before we can use the right hand rule, we have to find I perpendicular.
Oh, I see. I perpendicular is well, is 0. Theta is 180.
Right, don't confuse I and theta.
Yeah.
Right, so I perpendicular here is
0.
because I is anti-parallel to B. Well, when two things are anti-parallel, the component of I that is perpendicular to the other thing doesn't exist.
Yeah.
It's 0. So if one vector is either parallel or anti-parallel to the other vector, the component of one vector that's perpendicular to the other vector doesn't exist. It's 0.
Mm-hmm.
So what was the answer to my question?
There's no force.
Yeah, so it doesn't have a direction.
Yeah.
All right. So, so notice what happened here when you tried to use the right hand rule without thinking about I perpendicular separately. Well, you tried to say, gee, my fingers should be pointing out of the page and my palm should be pointing into the page, and your hand won't do that.
Yeah.
So basically, if you try to use the right hand rule and you break your hand,
yeah.
that is a signal that you forgot to think about I perpendicular separately. So that messes students up a lot.
Okay.
Remember, the whole right hand rule is premised on the idea that you're focusing on things that are perpendicular to each other, not parallel to each other. Okay, so this is just one more argument for not forgetting that what we care about is not I, but I perpendicular. We should actually write that down before we use the right hand rule. Just like for a moving charge, we should write down QV perpendicular before we use the right hand rule. And if I perpendicular or V perpendicular is 0, then there's no point using the right hand rule because there's no force at all. So we only use the right hand rule if the perpendicular component is non-zero. We only use the right hand rule if the perpendicular component is non-zero. Otherwise the force is 0 and it doesn't have a direction. Okay. Something else I wanted to mention. These formulas you must use SI units because otherwise you won't get an answer in newtons over here. So for example, if they give you a charge in microcoulombs, you got to put that into regular coulombs. Or if they give you a charge in millimeters per second, you got to put that into meters per second. Or if they give you something in millitesla, you got to put that into regular Tesla. In fact, all the formulas in that handout have to be used in SI units. All those formulas, you have to use SI units. All right, well, logically speaking, what do we have left? Well, we've dealt with this part of the flowchart. Now we have to figure out how to figure out the magnetic field from source charges. And we have to figure out how to figure out its direction and how to figure out its magnitude. All right, now actually remember that we just saw how to find the force on an individual moving charge or on a current. But actually over here, we're only going to focus on currents. For an introductory course, we're not going to focus on how individual charges can create a magnetic field. We're only going to focus on how a current can create a magnetic field, even though it could theoretically have just been a single charge. All right, so here's the version of the right hand rule that we're going to use here. Once again, unfortunately, there's many competing right hand rules out there, so you might see other people using different ones. This is the one I've had the most luck with. Now again, many instructors teach a right hand rule here where you curl your fingers, but I really haven't had good luck teaching people that. So we're going to deal, this is, you're supposed to keep your fingers straight in this right hand rule. We're going to use a right hand rule. So both of our right hand rules are going to keep your fingers straight. That way you don't need to think about them differently. So we should not be making our fingers like this. We should just be holding our fingers straight for this particular right hand rule. Notice that one of the right hand rules was about your fingertips and one was about your finger pads. So let's review these anatomical terms that I kind of just made up. What are these? Finger pads or fingertips? And what's this? All right, so this is what I mean by the finger pads. It's the fleshy part that's opposite to your nail. And the fingertip is this thing at the tip. So here we're dealing with the pad, so we'll just have to memorize that. One thing we should just memorize is that magnetic field lines always form loops. We should just memorize that. Magnetic field lines always form loops, which means they don't start or stop because they form a loop. So this is, the purpose of this is to tell us the direction of the magnetic field at different points on the loop. Why am I calling this IS? Well, now we're treating this like a source current because it's the source of the magnetic field. So here we have a current. Remember, we should think of this as a current that's coming out of the board. And now let's try to figure out what the magnetic field would be over here. Yeah, this is always tricky. It's hard now to indicate a position because I don't want to make this be a dot. All right, for the time being, I'll put an asterisk here. All right, so we want to figure out the magnetic field over here. So let's go through this together. Your thumb represents the current. Your finger pads represent the field. Now, the first thing we have to do is orient our hand so it looks like the board. That means I'm going to put my thumb here to represent the current.
Okay.
And now, where should I put my fingers? Should I put my fingers above my thumb, to the left of my thumb, below my thumb, or to the right of my thumb? Well, I happen to be interested in a point that is above the current. So I should put my fingers above my thumb, because that will tell me about the direction of the magnetic field at that position. All right, well now, what direction are my finger pads pointing in?
To the left.
So now we know that the direction of the magnetic field at this point is to the left. Okay, so I tried to spell those things out there on the handout. So one thing is you can't use this until you put your fingers in the correct position relative to your thumb. The thumb should be where the current is, and the fingers should be the point where you're trying to figure out the magnetic field. Let's look at some more examples of that.
So that star that you put there on a test, what will that be?
Well, they might simply say, what is the direction of the magnetic field at a point that is above the current?
I see.
Or they might, they probably wouldn't use a star, they would use a dot. And they might call that point A. And they would ask, what is the direction of the magnetic field at point A?
Okay.
And they expect you to realize that this is not a dot that represents coming out of the page. It's just a dot to label this point on the page.
Mm-hmm.
So they'll have to give you some way of telling you what point on the page they're interested in. Well, let's figure out the magnetic field over here.
Okay, so I is coming out of the board.
Right?
My finger, I'm pointing my hand in the direction of that.
Yeah, I can't keep my fingers up here because that would be above the wire.
Mm-hmm.
I don't want to put them over here because that would be to the right of the wire. I need to put my fingers to the left of the wire because I'm focusing on a point that's to the left of the wire.
Now my pads are pointing down.
There you go. So the direction of the magnetic field over here is down. By the way, what's the direction of the magnetic field over here?
The same.
You can see it's going to be the same from the same right hand rule.
Mm-hmm.
Let's figure out the direction of the magnetic field over here.
Okay, so the same thing, your thumb's pointing out, your fingers now point.
Now I got to put my fingers below the thumb. Good.
And so my pads are pointing to the right.
Good. Right over here.
Okay, so now my thumb is still pointing out,
Right?
my fingers are pointing to the right, and my pads are pointing up.
Now my finger pads are pointing up. Good. How about over here?
Okay, so now my thumb is still pointing out.
Right?
My fingers are pointing sort of diagonal.
Yeah, kind of northeasterly from my thumb.
And my pads are pointing like up and to the left.
Well put, up and to the left. So now my fingers here are to the northwest of my thumb, and pads are pointing up and to the left.